Hi guys, today I'm going to talk to you about limiting reactant problems and go through a couple of examples. This is set up to go through two examples. If you feel like you understand it the first time, don't worry about watching the second one, but if you think you could use an extra bit of help, I would encourage you to go ahead and watch it all the way through. So, limiting reactant problems have to be done if you are given a problem in which two numbers are given. So for every single problem that we've done so far, only one number has been given. And I told you that the first thing you should do is, number one, balance the equation, and then number two, look for the number. I just said number a lot of times. So in this case, when you go to look for the number, there are two numbers. We have 5.00 grams of aluminum and 5.00 grams of copper 2 chloride. So how do you know which one to use? So something to point out, this problem is different than the others because two numbers are given. So in order to solve this, we have to figure out which one of these is the limiting reactant. Whichever one is the limiting reactant will run out first, and at that time the reaction stops. So however much product has been made at that point is what is called a theoretical yield. So as we solve these stoichiometry problems, the theoretical yield is what the math tells us. It's the maximum amount of product that will form if all conditions in the lab setting are perfect. It's a mathematical calculation. So if you go to carry this out into the lab, if all conditions go well, if the reaction goes to completion, if you don't lose any of the new product down the drain through the decanting process, or if you don't get some impurities in there that may be causing extra weight that doesn't belong there, the theoretical yield is the theoretical amount that you could possibly form if all conditions in the lab go well. So the actual yield is how much is actually collected in the lab. So a calculation that can be done is called the percent yield, where you take what you actually collect in the lab. So this is the actual yield is the experimental amount divided by what the math tells us times 100. And an ideal percent yield is to get as close to 100% as possible. If you end up getting over 100%, it is not theoretically possible to produce any more than what you could theoretically produce, so there has to be something extra there that's causing the mass to be more. So close to 100 is what we're striving for. All right, so here's the problem set up again. This is what is the limiting reactant if 5.00 grams of aluminum, notice 3 sig figs, reacts with 5.00 grams of copper 2 chloride in a single replacement reaction. How much copper will theoretically be produced? Okay, so for this, I've set up the equation where we have our aluminum combining with the copper chloride to produce copper and aluminum chloride, and it is already balanced here. So if you look at the instructions down here, how to determine the limiting reactant. I'm going to activate the pen here, and I want it to be blue today. Here it says calculate the amount of product, either in grams or moles, that would be produced from each reactant. Whichever reactant gives the least amount of product is the limiting reactant. This amount, it's kind of hard to see there, is called the theoretical yield. So we have two numbers, which means we have to do two calculations. So for the limiting reactant problem, calculate the amount of product. The product we're interested in here is copper. So this is going to be the B in each of these calculations. Except now we have two starting substances. So two calculations, whichever one gives us the least amount of copper is the limiting reactant, and that amount is going to be the theoretical yield. So we'll set this up here. I had some notes where I actually had all of these equations written out. I probably threw them away. Darn it. Okay, I guess I will just go ahead and start fresh. Okay, so first calculation I'm going to write in red. In this one we have 5.00 grams of aluminum. So my starting substance is A, and I want to figure out how many grams of copper can be produced if we start with 5 grams of aluminum. Okay, so it's a mass-to-mass calculation, starting with grams of A. I've got that down. The next step is to look at 1 mole of aluminum, since that's my substance A, and put its molar mass, and it is 26.98 grams of aluminum for every 1 mole. Okay, I've done that step. The next step is the mole-to-mole ratio, and I have moles of substance A on the bottom, and we're looking for unit cancellation, which is why it makes sense that that's there, related to moles of substance B on the top, which is copper. Remember, these numbers are coming from the coefficients of the balanced equation, so 3 moles of copper for every 2 moles of aluminum. And our last step, I got my mole-to-mole ratio done. 1 mole of copper, and its molar mass is 63.55 grams. Okay, so grams of aluminum cancel, moles of aluminum cancel, moles of coppers cancel, and if we go ahead and do the, oh, my pen's out of control here, do the calculation, I have 5.00 divided by 26.98 times 3 divided by 2 times 63.55. And the calculator gives me, I'll just write it up and off to the side, 17.665. Oh, that's horrible. Okay. Now I have 3 significant figures here, so I need to round that to 3 sig figs. So 17.7 grams of copper could theoretically be formed if we start with 5 grams of aluminum. Okay, so let's see how many grams of copper we would produce if we start with the other substance. And for this, I will change the pen color to, how about green? Okay, so we have 5.00 grams of copper 2 chloride, CuCl2, and we are looking for grams of copper. So in this case, this is now my A, and my B is the same. Okay, so I need the molar mass of copper chloride. I know that chlorine is 35.45. Just do this off to the end. Copper is 63.55. Each chlorine is 35.45. And I'll use my calculator for this. 63.55 plus 35.45 plus 35.45 is 134.45 grams. And 1 mole of copper, my pen stopped working, copper chloride is 134.45 grams. Okay, next is my mole to mole ratio. I need moles of copper chloride here on the bottom and moles of copper on the top. And in this, it is a 3:3 ratio. 3 moles of copper for every 3 moles of copper chloride. And 1 mole of copper is 63.55 grams. And my grams of copper cancels. My grams of copper chloride cancels, moles of copper chloride cancels, moles of copper cancels. And I will plug this into the calculator. 5 divided by 134.45 times 3 divided by 3 times 63.55. And I get 2.363. And if I round this to 3 sig figs, that is 2.36. All right, so here is the question. How much copper will theoretically be produced? It's going to be whatever the lowest number is, okay? So when I combine these amounts, my theoretical yield my computer's running really slow, and for some reason it's causing this to not write very fast. Theoretical yield is 2.36 grams of copper. It's the smallest number. And if I identify this, this is my limiting reactant. Okay? So if the theoretical yield is 2.36 grams of copper and the amount of copper collected in the lab is 2.24 grams, the percent yield is going to be what was actually collected in the lab, 2.24 grams, divided by the theoretical yield, 2.36, I still have it up on my screen here, times 100, and we are looking at 2.24 divided by 2.36 times 100 is a 94.9% yield. That is a pretty high yield. It's close to 100, and it shows that little was lost, and also that the reaction went to near completion. Okay, so that's the end of the first reaction, and I will go on with another one. Okay, here's another limiting reactant problem. If you don't have time, stop watching. Otherwise, if you want to get a little extra help, go ahead and watch. So this one's modeled after our stoichiometry lab, where we took the aluminum foil and put it in our copper sulfate, and we made copper and aluminum sulfate. Now, something about this, the copper sulfate used in the lab was actually copper sulfate pentahydrate. So what this means is that for in the molecular structure, if you have atoms connected in a crystalline lattice in a very ordered and organized way, in this lattice, there are water molecules that are just stuck. So if you were a water molecule and you're stuck in this crystalline lattice, you might have kind of a frowny face because you're stuck in there and you can't get out. Okay, so that's what this guy is. So for every 1 copper atom, every 1 sulfur atom, and every 4 oxygen atoms, there are 5 water molecules stuck in this. So when you go and get the mass of this, it has all those extra water molecules tied up in there. So if we're using copper 2 sulfate pentahydrate with the extra water, we have to include that in our molar mass. So there are 5 molecules of water for each formula unit. I thought my pen thing would go away. It means that if we calculate the molar mass, we have to take into consideration the 5 water molecules. So our 1 copper, 63.55, sulfur, 32.07. We have 4 4 oxygens, giving us 16, and then the extra 5 water molecules for a molar mass of 249.72. All right, so here's the problem. If 2.00 grams of copper 2 sulfate reacts with 0.25 grams of aluminum, how much copper will theoretically be produced, and which is the limiting reactant? Okay, so with this, again, to get limiting reactant, calculate the amount of product that will be produced from each reactant. The product we're interested in is copper. So starting with 2.00 grams of copper sulfate, how many grams of copper will be produced? And also starting with 0.25 grams of aluminum, how many grams of copper will be produced? Okay, this is a mass-to-mass problem. Starting with the mass of the first substance, so copper sulfate in the first one is A, and our B is the copper. Okay, it's already balanced for you. So I've got my grams of A written down. The next step, 1 mole of the copper sulfate. Remember, with this molar mass, I have to include the extra water. So that was 249.72 grams. And next is my mole-to-mole ratio. Every 3 moles of copper sulfate, we have 3 moles of copper. And for every 1 mole copper, we have 63.55 grams. And my calculator does this. 2.00 divided by 249.72 times 3 divided by 3 times 63.55. I get 5.50897. So this is going to round to 3 sig figs, so 0.509 grams. All right, so let's look at, if we start with 0.25 grams of aluminum, my first step is the grams. Next I have 1 mole of aluminum, 1 mole of my substance A, and it is 26.9. I do not know why this is writing so bad right now. 26. 26.98 grams. My mole-to-mole ratio for every 2 moles of aluminum, I have 3 moles of copper. And 1 mole of copper is 63.55 grams. Punching this into the calculator, 0.25 divided by 26.98 times 3 divided by 2 times 63.55 is 0.883. So that will round to 0.88 grams. So how much copper will theoretically be produced? It is going to be this amount of copper, 0.509 grams, because this is the smaller number. Which is the limiting reactant? The limiting reactant is the reactant that produced the theoretical yield. Okay, so our theoretical yield is 0.509. This is the limiting reactant. So another percent yield calculation, if 0.45 grams of copper is collected from the actual lab, what is the percent yield? So, whoops. So if our actual yield, I think I'm on the wrong problem. Let's get back to that one. If 0.45 grams of copper is actually collected, my actual yield is 0.45 grams, and my theoretical yield from the previous slide was 0.509 grams times 100. 0.45 divided by 0.509 equals times 100. So we are looking at an 88% yield. I would say that's not necessarily a great yield. There were some groups in the lab that ended up getting a higher than 100% yield, and the only way that could have happened is if there was something else in, if this is the container that they collected their copper in, and there's your little copper bits. Theoretically, we should be able to get 0.509 and no more than that. So if there is greater than 100% yield, you can't just magically make more copper. It means that there are some foreign bits in that that are causing a higher yield than what could theoretically be possible. So those are my examples of limiting reactant problems and using theoretical yields and percent yields and actual yields. And again, this is the type of problem that if you see two numbers given, you have to figure out which one is the limiting reactant, and you solve two problems. Choosing the same product, whatever product you're interested in, whichever of the reactants gives you the least amount of product, that is your limiting reactant, and that amount is your theoretical yield. All right, thanks for watching.